Welcome to the Deep Dive. I'm your host, and you're here because you have that constant nagging desire to learn something fascinating.
Right, something that actually makes you see the world differently.
Exactly. But, I mean, let's be honest, you absolutely do not have the time to sift through the endless sea of information overload to find the good stuff.
No one does these days. It's just too much.
Yeah, we totally get it. That's our mission today. We're going to explore a completely unexpected and frankly delightful intersection of two very different disciplines. We're looking at what happens when the incredibly meticulous, highly analytical mind of a software engineer.
Which is a very specific type of mind, by the way.
Oh, absolutely. What happens when that mindset is applied to the deeply organic, somewhat chaotic world of botany and fish keeping?
It's a really fascinating contrast. Because, on one side, you have the rigid binary logic of computer code, where everything has a specific function and an expected output. And then on the other side, you have the absolute wildness of a backyard pond, where biological variables are just constantly shifting.
Right. And today's deep dive is built on a specific journal entry from a massive online archive. It really gives us a front row seat to what happens when those two worlds collide.
It definitely does.
So the source material today comes from a blog located at kianm.org. Specifically, we are looking at a post dated March 5, 2026. Now, you might hear the phrase gardening blog and immediately picture some highly curated aesthetic photos of blooming roses or perfectly manicured lawns.
Yeah, the typical influencer stuff.
Exactly. But this is not your everyday run-of-the-mill influencer gardening page.
Far from it. What we're diving into today is a uniquely transparent window into a highly documented process of biological trial, error, and adaptation. I'd argue it's really a masterclass in observation.
Oh, I'd agree with that.
This is a person treating the natural world with the exact same rigorous documentation standard that a senior developer might apply to, say, building a complex software system.
Or tracking a really persistent bug in a code base.
Right, exactly.
And the author of this journal, he signs his posts simply as Ang, and he describes himself right at the top of the site as an old software plumber, which I just think that phrase paints such a great picture.
It really does. Because a plumber isn't just writing flashy new code or designing slick user interfaces.
Right. They're in the trenches, they're fixing leaks, connecting legacy systems, and making sure the underlying architecture actually works under pressure.
And Ang writes that he spends his nights tinkering with free Libre and open source software.
Often abbreviated as flawless.
Yes, flaws. But to fully appreciate the context of this deep dive, you really have to understand the sheer scale and the philosophy behind his entire archive.
Yeah, let's talk about the numbers, because they are wild. The volume of his documentation is genuinely staggering, especially for a personal project. Ang has been logging entries on the site since at least 2011.
That's over a decade of constant documentation.
And this isn't just an occasional weekend update. In 2024 and 2025 alone, there were over 730 posts each year.
Which averages out to 2 a day.
Exactly, 2 posts a day, consistently. But the volume isn't even the most interesting part, is it?
No, it's the methodology. He is like a modern-day Renaissance hacker. You look at the tags on the site, and it's this wildly diverse mix of disciplines.
Right, alongside highly technical entries like notes on Haskell programming, part 76.
Or deep dives into Erlang, Go, and Rust.
Yeah, you'll find incredibly detailed ongoing series on entirely different topics. There are notes on dieting, part 115, entries on meditation, guitar, and even beta spawn logs.
If we connect this to the bigger picture, you start to see the underlying philosophy driving the entire site. Ang approaches all of his personal hobbies, whether it's managing his diet, learning an instrument, or breeding betta fish, the exact same way he approaches open source software development.
How so?
Well, he meticulously logs versions of his daily life. Those part numbers, like part 76 or part 115, those are essentially software version releases for his own personal experiments.
That makes so much sense.
Right. He's tracking the bugs in his life. And a bug might be a leggy seedling in his garden, or a plateau in his weight loss, and he's thoroughly documenting the solutions for the public to read. It is essentially an open source approach to living.
And he clearly lives and breathes that open source ethos beyond just his own writing. Right on the site, he explicitly lists his support for major open source and digital rights advocates. He highlights the Electronic Frontier Foundation, the EFF,
The Free Software Foundation, the FSF.
yeah, and the Tor Project and Wikipedia.
And those organizations, they're fundamentally built on the idea that information should be free, transparent, and accessible. so that a community can collectively iterate and solve problems together.
Mm.
By explicitly listing them, Aang is signaling that his backyard pond experiments aren't just private diary entries. He is releasing his raw data, his successes and his failures, into the wild so that anyone else trying to breed a specific fish or grow a specific plant can learn from his source code.
Okay, let's unpack this. We are zooming in on one very specific piece of that source code today. It's an entry titled Notes on Fishkeeping, Part 204.
Just pause and think about that number for a second. 204 distinct, documented iterations just on his fish-keeping hobby.
It's incredible dedication. So the primary subject of this specific entry is a plant known as Water Pennywort, or by its scientific name, Hydrocotyle verticillata.
And using the scientific name there is a great subtle indicator of that analytical mindset at work. He isn't just referring to it as some random pond weed. He's identifying the exact biological hardware he's testing.
Right, setting the parameters.
Exactly. And water pennywort is a really fascinating species. It's visually distinct. It has these small, umbrella-like leaves that branch off a creeping stem.
In this entry, Aang lays out his primary goal. He's continuing an experiment that he actually started back in a previous entry, Part 193. He is trying to adapt this water pennywort to live in the upper sections of his outdoor ponds.
Specifically, he wants it to survive as a semi-aquatic plant, growing out of the water and into the open air.
And this is where the core conflict of the experiment arises. Because water pennywort is highly versatile. As Aang notes in his journal, this species can actually survive fully submerged underwater.
Which is how it often grows in its natural habitat, or in standard home aquariums.
But in his attempt to adapt it to a semi-aquatic state at the pond's surface, he hits a major snag. He includes documentation showing that some of the older leaves are turning brown and completely rotting away.
Right. He notes that the overall results of the experiment are promising so far, but those rotting leaves are a glaring bug in the system. The plant is clearly struggling with the transition.
So applying this hyper-analytical open-source mindset to a backyard pond, what does that actually look like when things go wrong? Why would a plant that is perfectly capable of surviving completely underwater suddenly start rotting when it's just brought up to the surface?
Aang breaks this down into two distinct diagnoses. The first one is all about environmental shock. And to really understand it, we have to look at the cellular level of those older leaves.
Okay, lay it on me.
Think about it from the plant's perspective. These older leaves grew and developed entirely submerged in the pond. They were physically and structurally built for an underwater world.
Wait, but don't leaves basically function the same way whether they're underwater or in the air? They still need light and carbon dioxide to survive, right?
They do need the same basic inputs, absolutely.
Right.
But the hardware they build to get those inputs is completely different depending on the environment. Terrestrial leaves, the ones growing out in the open air, they have to deal with the constant threat of drying out.
Because the sun and wind just strip the moisture right out of them?
Precisely. So to combat that, they develop a waxy outer layer called a cuticle to seal the moisture in. They also rely on tiny pores called stomata, usually located on the underside of the leaf, to open and close. That allows them to take in atmospheric CO2 while minimizing water loss.
Oh, I see. So an underwater leaf doesn't need to worry about drying out at all.
Exactly. A leaf that develops fully submerged doesn't bother building a thick, waxy cuticle because water retention just isn't an issue. It's entirely surrounded by water.
That makes sense. It would be a waste of energy to build it.
Right. Furthermore, its method of respiration is different. It's pulling dissolved CO2 directly from the water around it, often without the same dense network of stomata that an aerial leaf requires. Its biological systems are hyper-specialized for a very specific aquatic environment.
And then suddenly, Aang pulls those highly specialized submerged leaves up into the open air.
And it is an instant shock to the system. Moving from that fully submerged environment to a semi-aquatic open-air state means the plant faces a massive, sudden shift in its reality.
Because those older leaves just don't have the right tools anymore.
Exactly. They don't have the waxy cuticle to protect them from the dry air, so they immediately start losing moisture. On top of that, they are suddenly exposed to atmospheric CO2, but they don't have the optimized cellular structure, the right stomata density, to process it efficiently.
It's a lot like taking a complex software application built specifically for an old legacy operating system and suddenly forcing it to run on a completely different modern framework. The old code just crashes because the dependencies are all wrong.
That is a perfect analogy. The environment changed entirely too rapidly for the legacy hardware, the old leaves, to adapt.
Right.
Because the physical structure of a leaf is relatively fixed once it's fully grown. It can't just spontaneously generate a waxy cuticle after the fact. So, unable to cope with the shock of the open air, those older leaves fail to thrive, eventually browning and rotting away.
Here's where it gets really interesting. The open air and the lack of a waxy cuticle aren't the only things causing these leaves to decay. The plant isn't just passively dying from exposure.
No, not at all.
There is an active internal biological mechanism at play here as well.
That's right. Ang outlines a second reason for the browning leaves, noting it's a very common issue for various plants, especially when propagating by cuttings. It really comes down to nutrient deficiency and highly calculated resource management.
Resource management by a plant.
Yes. In botany, this process is known as senescence, which is essentially programmed cell death.
Wait, so if the plant is already stressed and has limited resources in this harsh new environment, why does it actively kill off its own existing leaves? Wouldn't it want to keep as much surface area as possible to capture sunlight?
You'd think so, intuitively. But actually, keeping those failing leaves alive is a massive drain on the plant's energy reserves. The plant is operating on an incredibly efficient internal algorithm.
Okay.
As it tries to survive the shock of the new environment and actively reach upward to grow new semi-aquatic leaves, it realizes it has limited chemical resources available, so it actively cannibalizes itself.
It is intentionally shutting down the old growth.
Precisely. And it has to do with how certain nutrients move within a plant structure. Nutrients like nitrogen and phosphorus are what we call mobile nutrients. This means the plant has the ability to move them around its internal vascular system to wherever they are needed most at any given time.
Like a logistics network.
Exactly. So when the water pennywort realizes its older, submerged leaves are failing in the open air, it considers them a sunk cost.
So it just cuts its losses.
It does way more than cut its losses. It liquidates the assets. The plant literally begins breaking down the chlorophyll and the mobile proteins in those older leaves.
Wow.
That is actually why they turn brown or yellow in the first place. The green chlorophyll is being systematically dismantled. The plant then pipelines all of those salvaged nutrients straight up the stem to fund the development of new aerial adapted leaves at the top.
Man, if we look at this through the lens of our old software plumber, the plant is essentially deprecating an old feature to free up system memory.
Yes, that's exactly what it's doing.
It realizes the submerged leaves are an outdated process throwing error codes left and right. Instead of wasting processing power trying to keep a failing system running, it purposefully shuts it down. It writes all of that memory to power a brand new high-priority application, the new upward growth.
It's a ruthless, but highly effective survival strategy. The plant is managing its own internal bugs by deprecating old hardware to ensure the core system survives the transition.
That is amazing.
What's really fascinating here is how clearly this illustrates the sheer resilience and efficiency of biological systems. It isn't just passively wilting and giving up. It is executing a highly coordinated reallocation of chemical resources.
So what does this all mean for you listening right now? What's the big takeaway from Ang's pond experiment? Well, first, we've gained a much deeper understanding of the dual challenges that plants face when they're forced to change environments.
Right. They have to survive the external shock first. The sudden shift in water conditions, the lack of a protective cuticle, the dramatic change in CO2 processing.
While simultaneously managing a complex internal resource shift, actively breaking down old cells to pipeline mobile nutrients toward new growth.
But beyond the fascinating botanical science, there is a profound lesson here about the value of observation and transparency. Think about the depth of understanding that comes from this level of meticulous tracking.
Yeah, because Ang isn't a professional botanist.
No, he's a software engineer tinkering in his backyard at night. But by treating his personal hobbies with the same rigorous, documented, open-source approach that he applies to a complex code base, he yields these incredible insights.
It really makes you wonder what we could all learn if we applied just a fraction of that open source mentality to the everyday things around us.
Right.
What if we started tracking the bugs in our own habits, logging the details of our personal experiments, and actually paying close attention to the mechanics of the transitions in our own lives?
It completely changes your relationship with the world around you. You stop seeing failures as just bad luck, and you start seeing them as valuable data points. And this raises an important question, one that I think serves as a perfect final thought for you to mull over.
Let's hear it.
If you scroll all the way down to the bottom of Aang's site, past the thousands of meticulous journal entries, past the Haskell programming notes and the beta spawn logs, you reach a standard footer disclaimer. It reads, "Opinions expressed here are my own. I cannot guarantee the accuracy or completeness and will accept no liability for any loss or damage incurred."
The classic boilerplate software industry disclaimer. You see it on almost every personal tech blog or open source repository out there.
You do. But I challenge you to think about how perfectly that standard legal disclaimer applies to nature itself.
Oh, that's interesting.
When we decide to tinker with biological systems, whether that's something as massively complex as agricultural engineering or something as simple as moving a water pennywort from the bottom of a backyard pond up into the open air, nature offers absolutely no guarantees.
None at all.
There are no warranties in the wild. Nature accepts no liability for how our experiments unfold. The plant will do what the plant's internal algorithm dictates, whether we understand it or not. Ultimately, we alone must bear the responsibility and the liability for the changes we introduce into the system.
Nature accepts no liability. That is a powerful framework to carry with you. Thank you so much for joining us on this journey today. We hope this deep dive has given you some new mental models to play with, whether you're trying to debug a piece of open source software or just trying to figure out why your houseplants keep dropping their leaves.
Keep observing the data points around you.
Keep questioning the systems, and we'll catch you on the next deep dive.